Utility poles can sometimes look pretty complicated, but all of the crossarms, insulators, and guys that utility poles carry are there for a reason. This program will explain what those reasons are and how they determine the type of equipment that goes on a pole and the way it's arranged. The program will also show you how to frame a pole, that is, how to install crossarms and other conductor supports, as well as insulators. In addition, you'll see how to support a pole with guy wires that connect it to an anchor installed securely in the ground. The main function of a utility pole is to support conductors. Now, conductors are heavy, and they can pull on a pole with a lot of force. The equipment on a pole that supports the conductors must be constructed carefully to be able to resist these forces. So in this first part of the program, we're going to talk about 3 basic pole construction types and how they're affected by conductor forces. Probably the most familiar construction type uses crossarms to support the insulators and conductors. The second type doesn't use crossarms. It's called armless construction. Armless construction can use a variety of other devices to support conductors, such as fiberglass rods or insulators attached directly to a pole. The third type is vertical construction. Insulators are attached directly to the pole in a vertical line, one above the other. Now, there are a lot of variations on these basic construction types depending on the situation. The examples you're going to see in this program may not be the same as those used in your company, but the important things to remember are the reasons why a pole is built or framed the way it is. Basically, a pole is framed a certain way in order to perform certain functions. It has to be able to support the weight of conductors and resist their pulling force. It must maintain the proper spacing between conductors in order to provide the right amount of electrical clearance, and enough working clearance to let a lineman work safely. It must allow enough room for other equipment, like transformers, and any other utilities present, like telephone and cable TV lines. And it must be framed so it'll maintain adequate clearance between conductors and trees, buildings, and streetlights. As we said, the main function of utility poles is to support conductors. So let's take a closer look at this function and see how it affects styles of construction. When a pole is framed, the components that the conductors are attached to have to be selected and put together carefully in order to be able to withstand the strong forces that the conductors can exert. Conductors exert 2 basic forces on the components of a pole. One is the weight of the conductor wire. This force acts straight down. The other is the strain or pull put on conductors to keep them elevated and provide clearance below. This force acts in the same direction as the wires. Now, the forces that conductors exert can change from one pole to the next, depending on several factors: the angle that the conductors make with the pole, the length of the conductors, and the weight of the conductors. For example, the least amount of force is placed on a pole and its components when the conductors are in a straight line. In this case, there's no force from conductor strain. The strains from the wires stretching off in either direction cancel each other out. The insulators, their pins, and the wooden crossarm they sit on are strong enough to withstand the weight of the conductors resting on them. Other conductor arrangements can put much more strain on a pole. For example, conductors leading from a pole at an angle will put a side strain on the pole in addition to the conductor's weight. If the conductors deviate only slightly from a straight line, the side strain or lateral strain will be small, and the pole and its components will be strong enough to resist it. But the lateral strain quickly increases as the conductor angle becomes sharper. Even a moderate bend in the conductors can create enough lateral strain to eventually pull a pole over. So the lateral strain from angled conductors usually has to be resisted in some way. This is generally done with a guy wire. We'll talk about them in more detail later in the program. A conductor can only be bent around an insulator so far before it becomes unsafe. Too sharp a bend could seriously weaken the wire and pull too hard on the insulator. So when a sharp conductor angle would put too much strain on the wires, they're dead-ended and connected by jumpers. An angle sharp enough to require dead ends normally needs a guy wire to resist the strain of the conductors. Angled conductors are not the only source of unequal strains on a pole. Conductor spans of different lengths will also put an unbalanced pull on one side of a pole. The extra strain may require a guy to offset it. Well, we've seen some of the principles underlying pole constructions and the functions that poles and their components have to perform. Those functions are to support conductors and withstand their pulling strain, maintain proper spacing between conductors, and maintain clearance from other objects such as streetlights, buildings, and trees. In the next part of the program, we'll take a closer look at the details of 3 types of pole constructions and see how they're influenced by the specific functions they have to carry out. The last part of the program introduced you to the 3 basic construction types: cross-arm, armless, and vertical. In this part of the program, we're going to go into the specifics of how the 3 basic construction types are modified to suit different situations. Keep in mind that while your company may do things somewhat differently from the examples we show you, the principles are basically the same. Let's start off with cross-arm construction. Most wooden cross-arms are approximately 4 inches thick and 8 to 10 feet long. Thicker arms may be used when necessary. Holes drilled through the cross-arms hold the insulators. The insulator pin or mounting bolt fits through the hole and is secured with a nut on the other end. A through bolt normally attaches a cross-arm to a pole. Braces keep the arm straight. That is, they keep it from tilting to one side or the other. Braces may be essentially a pair of flat metal straps or a single V-shaped piece of angle steel. Wooden braces are sometimes installed instead of metal ones. They're often used for medium to higher voltages to minimize current leakage or tracking along the braces. Tracking could occur at these voltages with metal braces, since metal is a far better conductor than wood. In some cases, however, the conductor weight may be too much for a single cross-arm. For example, if the wire span length is unusually long, or the conductors are large and heavy, so the basic single cross-arm construction is modified to make it stronger. That's usually done by doubling the cross-arm to make it strong enough to handle the extra weight. But a doubled cross-arm requires additional modifications to the basic cross-arm construction. For example, another set of insulators may be added to help support the conductor weight. The second set also keeps the conductors away from the second cross-arm, and they reduce the strain on each conductor by distributing its weight over 2 points rather than 1. Extra bolts are needed to attach the double cross-arms to each other. They're designed to hold the cross-arms securely at a distance from each other equal to the thickness of the pole. Besides changes made to handle the extra weight, other modifications are often needed to handle additional strain forces from conductors. An angled conductor, for example, exerts a lateral strain which could put too much stress on the tie wire and break it. One modification used to handle small lateral strains is to tie the conductor on the side of the insulator. This puts the lateral strain against the insulator rather than on the tie wire. This technique should only be used when the downward strain is not strong enough to pull the conductor down. Special insulator pins that tilt against the strain may also be used to resist lateral strains. Another technique for resisting the strain of conductors is to use post insulators. They're thicker and stronger at the base than pin insulators. And the base of a post insulator sits directly on the cross-arm, which braces it against a pull to the side. Post insulators are often used to support heavy conductors because of their greater mechanical strength. Additional modifications to the basic crossarm configuration are needed at dead ends, where conductor strain is at a maximum. Crossarms are usually doubled at dead ends to handle the strain. But sometimes doubling isn't enough. A long span or extra heavy conductors may require tripled or even quadrupled crossarms to withstand the force. In some cases, thicker crossarms are used for the same purpose. Or double arms may be stacked one above the other instead of side by side. The strong force from the pull of the conductors at dead ends puts the maximum strain on insulators. So dead-end suspension insulators designed to withstand this force are used rather than pin or post insulators. As we mentioned earlier, utility poles have to be framed to carry out other functions besides simply supporting conductors. One important function is to provide enough clearance to keep the conductors away from nearby objects. Poles near buildings or trees, for example, may not have enough room for a conventional crossarm that extends out on both sides. In that situation, a sidearm or alley arm may be used to provide the needed clearance. Alley arms are also used for other purposes too. One common function is to hold conductors off to the side of a pole to keep them closer to a straight run. An alley arm can reduce the bending that would occur if the conductors had to lead all the way over to the pole. Well, all of these principles apply to the other types of construction as well. Let's first look at the components used in armless construction. Then we'll see how they can be modified. Armless construction is usually used because it requires little maintenance. The fiberglass rods or other supports for the insulators don't rot or split like wood. The center phase on this type of armless construction may be placed next to another phase on a lateral rod, or it may extend directly up from the top of the pole. Another type of armless construction support is a heavy fiberglass or steel bracket that's sometimes called a chicken wing because of its wing-like shape. The bracket base is through-bolted to the pole at the top and the bottom. Armless construction doesn't have to have a supporting structure for the insulators, of course. Post insulators are sometimes fastened directly to the pole in armless construction. Just as with crossarm construction, the components used in armless construction can be modified to handle additional strain or weight from conductors. They can be doubled, or they can be made stronger and heavier. The strain from the dead ends on this pole requires fiberglass rods that are thicker and stronger than those used for straight-run conductors. In this case, the center phase has been dead-ended with a suspension insulator attached directly to the pole. Insulators are also attached directly to the pole in the third type of construction we're going to talk about in this program, vertical construction. In vertical construction, however, the insulators are arranged in line, one above the other. The insulators used in vertical construction are often the horizontal post type. The base of this type of insulator is usually through-bolted to the pole at the top and bottom. Horizontal post insulators used with higher voltage conductors often have a clamp top. The clamp locks around a conductor to hold it firmly in place. Post insulators can be used with vertical construction as long as the conductor angle isn't too sharp. But sharper bends may require a suspension insulator able to take the additional side pull. This particular configuration is known as a running corner. The suspension insulators used in this case hold the conductors in a gentle curve that spreads the weight out over a larger area to keep the wires from flattening out. This is the main difference between this type of suspension insulator and those used on dead ends. Dead-end suspension insulators are attached to the ends of conductors. In some situations, a dead-ended vertical pole may have to be framed a little differently. For example, there's sometimes a danger that unsupported jumpers could swing against the pole under certain conditions. To prevent that, additional insulators may be added to hold each jumper away from the pole. These insulators keep the wind from blowing the jumpers against the pole. Well, we've seen a few examples of the many variations you may encounter when framing poles. You should be able to apply what you've seen here to the situations you'll encounter in your company if you take the time to think about the function of each component used to frame a pole. In the next part of the program, we'll take a look at some of the jobs involved in framing poles. The components on a pole can vary in many different ways, as we've seen so far in the program. The type of conductor supports, the use of guys, the spacing of the conductors, and the type of insulators all depend on what's required in a specific situation. The arrangement of these components is what framing is all about. There are a lot of techniques to learn in framing, so we're going to talk about it during the next two parts of the program. In this part, we'll look at some of the individual tasks that may have to be done to the pole itself, and we'll also see how pole hardware is installed. Then in the next part, we'll put those individual tasks together on some typical pole framing jobs. Let's begin this part of the program with the work that may have to be done on the pole. A pole may require some preliminary preparation, or it may be delivered ready for framing. For example, the tops of most poles are cut on an angle called a roof. This keeps water from collecting there and causing rot or cracks. A slant roof is simply a single-angled cut. A double-angled cut forms a gable roof. Pole roofs are generally pre-cut. Another type of cut often made in a pole is a flat surface for the crossarm to rest against. This surface is called a gain. It helps keep the crossarm from rocking back and forth after it's bolted to the pole. Most poles have at least one gain already pre-cut, but you may have to cut one in the field and drill a hole for the through bolt if there aren't enough in the pole. For example, you may have to add a buck arm to an existing pole. Remember that before working on a pole, you should always make your work area safe according to approved safe working practices. The location of the through-bolt hole should be measured carefully to make sure the arm is placed according to company specifications. Two lines should be drawn on either side of the hole location to mark a space the width of the crossarm. The gain is cut along these lines. The cuts should be no more than an inch deep, and the saw should be kept level so that the gain is even on both sides. Make sure to cut the gain on the correct side of the pole. For example, this buck arm gain should be at right angles to the existing crossarms. The wood between the cuts is then chiseled out to make the flat gain surface. Care should be taken to make the surface flat. A bump could keep the arm from seating correctly against the pole. Anywhere there's a gain, of course, there has to be a hole for the crossarm mounting bolt. A pre-cut gain often has a hole already drilled, but if it doesn't, or if you've just cut a new gain, you'll have to drill the hole yourself. The hole should be slightly larger than the through bolt to make it easy to insert. If you're using a standard 5/8 inch bolt, you should drill with an 11/16 bit. It's important to drill the hole in the center of the gain and straight through the pole. In other words, the hole through the pole should be perpendicular to the flat surface of the gain. Cut gains are common on wooden poles, but they're not the only kind in use. There's another type which doesn't require cutting, called a patent gain. It's basically a metal bracket that's curved on one side to fit against the pole and flat on the other side for the crossarm. There are several different types of patent gains. This one has teeth on the curved side to keep it from slipping against the pole. Other models also have teeth on the flat side. A patent gain also provides electrical continuity between the crossarm and the pole. If a crossarm becomes energized, current can arc between it and the pole and start a fire. But the metal gain provides a conductive path between the crossarm and the pole to prevent arcing. Whatever type of gain is used, most crossarms are mounted to the pole in the same way, with a through bolt. Now let's take a closer look at them and some of the other bolts used to mount crossarms, armless supports, and insulators. Through bolts are often machine bolts with a head on one end and threads for a nut on the other. Washers should always be used at each end. Machine bolts aren't the only type of bolts used to frame a pole. For example, double cross arms are usually held together with double arm or DA bolts. DA bolts are generally threaded along their entire length. To hold the cross arms apart, nuts are screwed down the DA bolt so they're inside each cross arm. Nuts on the outside hold the arms tightly against the inner nuts. Another way to hold double cross arms apart is with a spacer that takes the place of the two interior nuts. This one is simply a section of cross arm with a hole bored through it for a bolt. Either a DA bolt or a machine bolt can be used with a spacer. A different type of bolt is used to attach braces to a cross arm. It's called a carriage bolt. Many carriage bolts have a square shank under the head that's driven into the wood around the hole in the cross arm. This locks the bolt into the wood and keeps it from turning when the nut is screwed on. If there's no square shank, a washer is needed under the head. The pole ends of the braces are often held in place with a square-headed screw called a lag screw. In some companies, lag screws are driven into the pole with a hammer. In others, they're screwed into a pilot hole drilled partway into the pole. In some cases, company specifications may call for the braces to be through-bolted to the pole. That's sometimes done for double cross arms or when the braces have to support an extra heavy load, such as from longer cross arms or larger insulators and heavier conductors. Now, armless construction, of course, doesn't require braces, but the conductor supports themselves are still attached to the pole with through bolts. Fiberglass rods used as conductor supports may be attached separately to a pole or mounted on a single bracket. Bolts are also used to mount insulators, although some of the bolts used are a little different from the ones we've seen so far. For example, an insulator pin is basically a through bolt that goes through a hole in the cross arm, but it's flared in the middle to support it on the upper side of the arm. The nut can be secure with a lock nut. Now, this type is often called a PAL nut. It's shaped to fit over the curved surface of the main nut to keep it from coming loose. The glass or porcelain insulator is threaded inside. It screws down over threads on top of the pin. When used to support a center phase conductor, a pin insulator often sits on a ridge pin that's through-bolted to the pole. Pin insulators are also used with armless construction. The pin may be part of a bracket that's permanently attached to the fiberglass rod, or it may be screwed directly onto a fiberglass rod with a threaded end. Post insulators generally have a threaded steel insert in the bottom of the porcelain. The insert is screwed onto a post insulator bolt that's threaded on both ends. The porcelain spool insulators used for neutrals and secondaries are often mounted horizontally with a through bolt that goes directly through the spool and the pole. They can also be mounted vertically on a bracket that's through-bolted to the pole, especially with dead-ended conductors. Now, all of these insulators we've seen so far have been mounted rigidly, but the suspension insulators used for dead ends are a different story. Suspension insulators are usually hung loosely so they can orient themselves in line with the conductors they're holding. A rigid connection could bend from the strong downward conductor pull. Suspension insulators are usually hung from an eye that's either attached to a through bolt or is part of the through bolt itself. They can be connected to the eye in different ways, but the most common is with a pin. A cotter key keeps the pin from sliding out. Well, the insulators and other components we've seen can be put together in a lot of different ways depending on the job at hand. It may be possible to frame the entire pole on the ground before it's erected, or you may have to do it all while you're on the pole. In the next part of the program, we'll watch some poles being framed and see some of the techniques used to do it. In the last part of the program, we got a pretty detailed look at mounting the individual components used to support conductors on a pole. Now we're going to see how these components can be put together to frame a pole. Some of the techniques and equipment you're going to see may be different from your company's, but the principles involved and the reasons for using them are the same. Like most jobs, framing a pole should start off with a tailgate session to make sure everyone knows his responsibilities. The specifics of the job are explained and work assignments are made. On this job, the crew has to install a crossarm on a newly erected pole. For the most part, your company's engineering department decides the specifications for each pole. They're typically spelled out on a couple of different sets of diagrams and instructions. One is often called a construction print. It gives the pole location and reference numbers for company specifications about the pole. The other is a set of specifications that are usually on a separate sheet or in a manual. They show how the pole is to be built and what type and size of materials are needed. Now, there are often several things needed to frame a pole that aren't spelled out on a spec sheet. These are usually standard hardware items like nuts, washers, and bolts. It'll be up to you to figure out which of those items you'll need based on your own experience. One important item you're likely to have to figure out yourself is what size through bolts to use for the crossarms. A through bolt should be long enough to go all the way through the pole and crossarm without sticking out too far. Too much bolt extending past the nut can provide a point for static discharge that can interfere with radio and television reception, and a lineman could snag his clothing on it or injure himself. To calculate the right length, you have to add up the total thickness of whatever the bolt has to pass through. For example, suppose the pole is 8 inches in diameter. If a patent gain is used, it adds another inch. The crossarm adds 4 more inches, and the nut and washers require 1 more inch. With an inch or so protruding, the total bolt length should be around 15 inches, measured from below the head. Once you know what type and size of materials you'll need for the job, you can gather them together so they'll be ready for the lineman when he goes up the pole. This job will require a crossarm and braces, a lag screw, a through bolt, 2 carriage bolts, insulator pins, and a patent gain. They'll also need 3 insulators, which should be checked for cracks and chips. It's generally a good idea to do as much work as possible on the ground before a lineman goes up, so he doesn't have to wait on the pole. One job that can often be done on the ground is to frame out the crossarm, although depending on the situation you're in, it may not be possible to frame it completely on the ground. For example, on this particular job, it's been decided that the braces won't be attached on the ground. It's the lineman's preference in this case to leave them off until he's hung the arm. The carriage bolts, though, will be put in the arm. The nuts go on temporarily to keep the bolt from falling out. The lineman will add the washers later when he puts the braces on. The other bolt goes in the same way. Each insulator pin is pushed through the holes and a nut and washer put on. A lock nut is added to keep the main nut from working loose. The nuts aren't tightened until after the insulator has been positioned. When the insulator is screwed down tight, it should be lined up so that the slot in the top for the conductor is perpendicular to the arm. Then both nuts can be tightened. The insulator should be held while tightening so it won't change position. He'll also install a second insulator on the other end of the crossarm. It's been decided for this job that installing all 3 insulators would make the crossarm harder to handle. So the lineman will install the 3rd insulator after he's got the arm mounted on the pole. Now, there are a lot of other ways this job could be done. You may find when you do it that other methods work better. There are 2 basic ways to hang a crossarm. One way is to first put the through bolt in the crossarm and then push it through the pole. The other is to push it through the pole first, then slide the arm over it. With the second method, the safety strap can be hooked over the bolt head on the back side to keep it from sliding out when the arm is pushed on. This patent gain has a hole in it, so it goes on before the crossarm. Other types may have a slot that can be slid over the bolt after the crossarm's in place. A cross arm should be sent up a pole in a way that's most convenient for the lineman. That means that any hardware on the arm, like the carriage bolts for the braces, should be facing in the right direction, so the lineman doesn't have to turn the arm around. It also means that the lineman shouldn't have to support the cross arm by himself while he's taking off the hand line and maneuvering the arm into position. On this job, the hand line is tied around each of the two insulators. This way, the man on the ground can continue to hold the weight with the line around the lower insulator, while the lineman unties the upper one and pulls the arm into position. With the safety still holding the through bolt, the arm can be slid in place over it. A washer and nut are screwed on the end. The braces are sent up separately on this job, so they have to be bolted to the arm. The cross arm should be lined up before the braces are lagged to the pole. A man on the ground indicates when the arm is lined up. The arm can be lined up exactly horizontal, or you may want to lift one end slightly if it's going to support more conductors than the other side. The high side will settle later under the weight of the conductors. With the arm aligned, the braces are lagged to the pole. When driving a lag screw, your safety strap should be adjusted to let you swing freely with both hands. You should be leaning out far enough that you don't have to choke up on the hammer, but not so far that you have to reach. On this job, the third insulator is the last piece of equipment mounted. Framing a double cross arm is a little harder, but the basic principles of the job are pretty much the same. One additional point to remember with double cross arms is that both arms should be parallel to each other once they're in place. If you're using DA bolts on the arms, the nuts on them must be adjusted to the proper spacing so the cross arms will be the same distance apart as the pole diameter. Let's watch a pole being framed with double cross arms and see how it's done. Since pole diameter determines the cross arm spacing, the lineman has to measure it first. He's already made his work areas safe following approved safe working practices. One good measuring technique is to block the back of the hole with your hand and push a rule through until you hit it. The man on the ground will adjust the nuts on the DA bolts to keep the ends of the cross arms as far apart as the middle. This pole's diameter is 9 inches, so the distance between the outside of the nut and the cross arm should be the same. Both outer bolts are adjusted the same. He'll also install the carriage bolts and the center through bolt. The bolt holes on the other cross arm should be reamed out or drilled out to make it easier for the lineman to slide them over the bolts. The holes are often rough inside with wood slivers that can get in the way. The first double arm is installed pretty much the same way as a single arm. In this case, the through bolt is already in the arm, so it's pushed through the pole from the lineman's side. A nut isn't put on the through bolt yet because the other arm still has to go over it. The lineman swings around to the other side of the pole to put on the other cross arm. He has to slide each hole only slightly over the bolt ends at first so the arm will fit over them cleanly. He starts with one end, then the middle, and then the other end. A washer and nut are placed over the center through bolt first to secure the arms. Then the nuts are tightened down on the DA bolts. The arms should be measured to make sure they're the same distance apart at the ends as they are in the middle. If they're off, the nuts should be adjusted to line them up. The rest of the job is similar to finishing up a single arm. In this case, that means that the braces must be attached to the cross arms, the arms lined up, and the braces fastened down. Keep in mind that there are many different ways to hang a double arm besides the one we've shown you. In this part of the program, we've seen how single and double cross arms can be installed. In the next part of the program, we'll take a closer look at guys. We'll see several different types of guys and look at several different situations when guys are used. The pull from conductors can exert a lot of force on a pole. This force must be offset or balanced to keep from pulling the pole over. That's normally done with a guy wire. We're going to take a look at guys in this part of the program. We'll see what they consist of, when they're used, and how they're anchored. Guy wires come in different diameters or sizes to match different amounts of conductor strain. When the strain on a pole does require a larger guy, it may be necessary to install a stronger anchor as well. So it's important to follow your company's specifications on what size guy wire and anchor to use to counteract the conductor strain in each situation. The many different conductor arrangements possible in any system require many different guy arrangements. So we'll take a look at several of them. We'll look at guys that run from a pole to the ground, from one pole to the next, from a cross arm to a pole, and even a guy made from another pole instead of from wire. Probably the most common type of guy is the down guy. It's basically a wire running from an attachment near the top of the pole to an anchor in the ground. Down guys can be used in many different situations where strain must be offset. For example, down guys are often used to balance the strain of dead-ended conductors. This one is used at the termination of a line. If dead-ended conductors pull in two different directions, a separate guy may be needed to balance each one. In other cases, guys may be able to split the difference between the strains from two dead-ended conductors. Guys are also used to balance the pull of angled conductors that aren't dead-ended. When there's enough room, a guy is usually anchored at a distance from the pole equal to the height of the guy attachment to the pole. This is referred to as a 1-to-1 ratio between the height and the distance. This ratio makes sure that the guy leads away from the pole at enough of an angle to provide the outward pull needed to offset the conductor strain. Sometimes, though, the only place for an anchor is so close to the pole that the guy can't lead out at enough of an angle. For example, if there's a road or sidewalk in the way. In this situation, an iron pipe strut is sometimes used to lead the upper part of the guy out at a great enough angle to support the pole, while the guy's lower half leads straight down to an anchor close to the pole. This type is usually called a sidewalk guy. Down guys are sometimes installed in line with straight-run conductors. That's typically done if there's unequal conductor strain or if the conductor span in one direction is longer than the span in the other. The additional pull on the pole from the longer span is balanced by the guy. Conductors passing over railroads or highways sometimes have down guys to provide an extra margin of safety. If this line went down during a storm, it could cause a lot more damage than if it fell in a field. So down guys are used to back up the poles on either side. Down guys used in this situation are sometimes called storm guys. Multiple cross arms and stronger conductor supports may also be used in this situation. The different types of down guys we've been looking at anchor poles directly to the ground. But there's another type of guy that runs from one pole to another. It's called a pole guy. Pole guys may be used when the anchor for a down guy can't be installed near the pole for some reason. For example, if there's a road or pavement in the way. A pole guy leading from the top of one pole to the top of another is often called a span or overhead guy. A variation on the span guy is used to cross a road when there's no pole on the other side to connect a guy to. For example, this buck arm is guyed with a stub guy leading to a separate stub pole that's been erected across the street to support it. A down guy leading from the stub pole secures the entire structure to an anchor in the ground. Now, there's another type of pole guy used in some situations that doesn't always require an anchor. It's called an advance guy. An advance guy consists of a series of pole guys used when it's not possible to place an anchor anywhere near the pole needing guying. It's a little more complicated than the others we've seen, so let's look at a simplified illustration to explain it. Advanced guys make use of leverage to compensate for the lack of an anchor guy. Pole A needs guying to counteract the strain from dead-ended conductors. A pole guy runs down to pole B to a point that's high enough to maintain ground clearance. So far, it looks like an ordinary head guy. But pole B also has a guy leading from its top to pole C. The force on this guy is much less than the force on the first guy because the pole acts as a lever pulling the first guy. The process continues until the last guy in the row has so little force on it that there's no need for another guy. The conductor spans between poles used for advanced guying may be kept slack in order to keep the strains on them to a minimum. The advanced guys and the other pole guys we've seen all run from one pole to another. And of course, the down guys we saw before them run from a pole to the ground. Now let's take a look at a guy that runs from a cross arm to another pole. It's called an arm guy. This illustration shows an arm guy seen from above. There's an unequal strain on this cross arm because two wires are dead-ended on one side, so an arm guy connected to the next pole in line is used to offset the extra strain on one side. Now, most guys are under a good deal of tension because they're offsetting the strain put on a pole or cross arm by conductors. So guy wires have to be attached to poles very securely to be able to withstand that tension. Most guy wires are secured to poles with brackets held in place with through bolts. A loop or eye in the end of the guy wire is hooked over this type of bracket. Now, it may have occurred to you that there's the possibility of electrical grounding through a guy wire. After all, it's a bare wire usually running from a pole into the ground. Well, as it turns out, guys may be used as grounds in some situations. In others, they're protected by insulators to make sure they can't become paths to ground. It depends on the conditions that a company has to deal with in its system. For example, systems that have difficulty making ground often use guys as additional paths to earth. These guys can be connected at their upper ends to the regular pole ground. Systems that don't have any problem making ground may use ungrounded guys instead as a safety measure. One or more insulators may be incorporated in an ungrounded guy to isolate the part that's attached to the pole from ground. These particular insulators are thin fiberglass rods called strain insulators. They're designed to keep guy wires away from conductors and to provide additional working clearance. Strain insulators may also be made out of wood. There's another type of guy insulator that's made of porcelain. An eye in each segment of the guy wire passes through the holes. Although each wire eye passes through the other, the porcelain in between prevents electrical contact. The insulator design also provides a safety link in the guy. If the insulator ever broke, the interlocked eyes would catch and keep the guy intact. Now, there are some situations where multiple insulators are placed in a guy to keep from shorting the conductors on a pole if the guy should break. This is referred to as a broken guy condition. Multiple insulators are usually used when a pole is congested or has several circuits, and it's more critical to reduce the possibility of shorting. Let's use an illustration to explain the concept. This particular guy has a strain insulator and two porcelain insulators. If the guy wire broke, it would fall against the conductors, but current couldn't flow from one set of conductors to the next. The insulators would electrically isolate each section of guy touching the conductors. Well, so far we've talked about different types of wire guys: guy attachments, guy grounding, and guy insulators. There's another major component of most guy systems, of course, and that's the anchor. Let's take a look at one and see how a guy is connected to it. One common type of anchor is the expansion anchor. It has metal leaves that expand outward into the earth to secure the guy. Before they're expanded, The metal leaves fit in a tight grouping around the anchor shaft. This lets the anchor fit through a relatively small hole bored in the ground. When the anchor is at the bottom of the hole, a pipe or other device is used to pound the top of the leaves. The pounding forces the leaves open and into the surrounding dirt. There are also other anchor types such as the screw anchor, the dead man or log anchor, and the never creep anchor. We'll talk more about anchors in the next part of the program. Now, we saw earlier that the upper end of a down guy has to be securely attached to the pole in order to stand up to the force from the conductor strain. Well, the lower end has to be just as securely attached to the anchor. That's often done with an eye formed in the end of the guy with a prefabricated piece of wire called a guy wrap. To use a guy wrap, one end is threaded through the eye of the anchor shaft. Then each end is wrapped separately around the guy wire. The second end wraps in between the coils of the first. Connecting a guy wire to an anchor in this way is known as making up the guy. Another device used to make up a guy is the automatic dead end. A U-shaped end hooks through the anchor eye, and the guy wire slips through a hollow grip on the other end. When tension is released, the grip holds the wire firmly. We've spent most of this part of the program talking about wire guys, but as we mentioned earlier, there's another type of guy that's made from a wooden pole. Let's take a look at one. It doesn't look at all like the wire guys we've seen, but it does the same thing. It offsets the strain of conductors on the pole. This push guy, or brace as it's called, resists conductor strain by pushing against a pole rather than pulling on it. Push guys are used where there's no room for a wire down guy, such as when a pole is next to a road. They're usually attached with a hinged bracket that's through-bolted to both poles. Well, we've had a pretty detailed look at guys in this part of the program, how they're configured, how they're attached to poles, and how they're anchored. The next step is to see how to install a guy in the field. So in the next and last part of the program, we'll see one way to install a stub guy. We've seen many of the different components of a guy and some of the different devices used as anchors. So in this last part of the program, let's see how these components are put together when guying a pole. We'll first see a couple of anchors installed, then move on to the installation and tensioning of the guy wire. The job we're going to see will be to install a stub guy to balance the conductor strain on this pole. A road next to the pole prevents the use of a simple down guy. In this particular case, the conductors on the pole to be guyed are not energized. The location of the guy anchor is usually specified on the construction print. The distance obtained from the print can be measured with a tape. The tape should be stretched out in line with the conductor strain. When an anchor requires a hole, it may be dug with a power digger or by hand. Remember that whether digging by hand or machine, it's important to notify the proper authorities beforehand to make sure you won't damage underground cables or pipes. They'll use an expansion anchor on this job. It's important to line the auger up properly before digging so the hole will be in line with the guy wire. When viewed from the front, the auger should be in line with the pole. And from the side, the auger should be tilted back so it's in line with the guy that will lead down from the pole. The hole should be deep enough to leave around 10 inches or so of the anchor shaft protruding above ground. When the hole's been dug to the right depth, the anchor can be lowered in place. A heavy tool designed to slip around the shaft is used to pound the leaves open. It's often called an anchor breaker or anchor buster. The dirt is shoveled back in the hole and tamped down so the anchor won't pull loose. Now, in the last part of the program, we mentioned that the screw anchor is also commonly used to secure guys. So let's take a look at one being installed. A screw anchor doesn't require a hole. It can be screwed directly into the ground, either by hand or by machine. It's important to put pressure on the anchor to push it into the ground while the screwing action is pulling it down. This makes sure the screw doesn't simply turn through the earth without moving downward. This is called churning, and it can destroy the anchor's effectiveness. Churning can loosen the soil around the anchor to the point where it will pull out under pressure. Before a guy wire can be attached to an anchor, it has to be cut to the right length. Now, there are several ways the length can be determined. The distance from the attachment point on the pole to the anchor can be measured, or the wire may arrive at the job site pre-cut. The method used will depend on your company's policy. However you cut it, you first have to pull off a section. Guy wire may arrive at the job site on a feeder reel, a large spool, or in a bound coil. This bound coil, for example, lets you pull out a section of wire while the rest of the wire stays neatly wound up. Let's see how it's done. There's a very important rule to follow when working with guy wire. Keep it under control. Guy wire is stiff steel. If it gets loose, it can lash out in any direction. It could seriously cut someone if it hit him. Or if it's being unwound on a pole, it could fly out and hit an energized conductor. When pulling off a length of wire, you should make sure that it uncoils as it comes off the reel. This prevents kinks that could weaken the wire. When cutting it, make sure to keep the twisted strands that make up the wire under control. They can untwist or unlay when cut, so it's a good idea to tape the section to be cut. The tape holds the strands together so they don't fly apart. Guy wires cut to the right length can be attached to a pole in different ways. Two different methods will be used on this job. One on the head guy to the stub pole, and one on the down guy to the ground. Both are usually attached with the same through bolt. The head guy will be attached to an eye that's held on the other end of the through bolt, the nut. A curved washer is used because it can more evenly distribute the strain from the guy against the rounded pole surface. With the bolt pulled down tight, a lag screw is driven into the down guy attachment to keep it from rotating under pressure. The down guy can now be hung from the pole. A guy wrap on the end is simply looped over the guy attachment. The other end of the down guy will be connected to an anchor. We've already seen a couple of the devices used to attach guys to anchors, a guy wrap and an automatic dead end. The equipment used to install these devices can vary from one situation to the next, but the procedure is basically the same. Tension is put on the guy wire first with a hoist or block and tackle. Then the device is used to join the wire to the anchor. The procedure often has to be repeated in order to get the guy wires to the correct tension. Let's see one way to do the job with a stub guy. Several tools are needed for this job. It's often necessary to connect some sort of device temporarily to the anchor shaft to give the hoist something to pull on. The other end of the hoist will hook onto a wire grip. The grip should be placed high enough to leave room for a guy wrap. One end of the hoist is hooked to the grip, and the other end to the device around the anchor. The slack is pulled out of the guy wire before the guy wrap is installed. On this particular job, the guy will be pulled tight or tensioned later, after the head guy has been installed. For that reason, the guy wrap's position is only temporary at this stage in the process. The ends are left free so it can be unwound again. The head guy is attached from the pole being guyed to the stub pole. In this case, an automatic dead end is used. The head guy only has to be tensioned once on this job, since final tensioning will be done on the down guy. A man on the ground watches the pole as the lineman tensions the head guy. Tension is put on the head guy until the pole is vertical. When the pole's straight up and down, the guy wire is adjusted to remove the slack. If the guys in the system are grounded, the two parts of the stub guy are joined together to maintain electrical continuity. A connector joins the two wires together. The down guy is now tightened further for the final tensioning. Enough tension is put on it to pull the pole being guyed slightly beyond vertical, that is, to rake it. The reason for this is to compensate for any settling that may occur. If the pole is raked properly, it will gradually become vertical as it settles. You'll learn the right amount of rake by experience. When the pole's at the correct angle, the guy wrap can be reinstalled to hold it there. The ends are wound up all the way this time. The chain hoist, wire grip, and hoist attachment are removed, and the excess guy wire is cut off. Guys can be hard to see, so they're usually covered by a guard to make them more visible so people won't run into them. A guard should extend from the ground to about 8 feet up the wire. Guards usually have 1 or 2 straps or clamps to hold them on. The clamp on this one is simply screwed tight around the anchor. By offsetting the conductor forces on a pole, a fully tensioned guy creates a strong, balanced structure that should stay in place for a long time. Remember to keep the idea of balanced forces in mind whenever you're assigned to frame a pole. It will help you understand the reasoning behind the design of the pole you're working on. The better you understand the job you're doing, the better job you'll do. If you apply the principles you've seen here to your company's procedures and equipment, you should be able to do a safe and effective job of framing and guying poles.